Welcome back to part 4, everybody. Now, in the last video we took a look at pathfinding systems from a very high level, and we learned that a navigation graph must be compiled, normally at development time, that can be used at runtime by agents to perform path queries using search algorithms. We also saw just briefly how Unity provides us with a tool within the editor to build our navigation mesh. And we saw how we're also provided with the NavMesh agent component that we can add to our game objects, which will perform path queries and steering logic for us at runtime. Now don't worry, we're going to spend plenty of time getting our hands dirty with those components in the next video. In this video, however, I want to drill down and really understand the A-star search algorithm. So let's talk about some of the characteristics of the A-star search algorithm. Firstly, it's what's known as being complete. This means that if a solution exists, this search algorithm will find it. Also, a heuristic is used to score neighboring nodes as potential candidates for the next iteration of the search, and this significantly speeds up the search process. Essentially, it tries to visit the least possible number of nodes by selecting the next neighbor to step into based on how likely it is to take us to the target along the optimal path. Next, assuming an admissible heuristic, and we'll talk a little bit about what that means in a moment, it will always find the cheapest path. Finally, A-star will search with variable node costs. This allows us to mark regions of our game world as being more difficult or expensive to traverse than others. And we saw in the previous lesson just briefly that Unity supports this mechanism as well, allowing us to mark different regions of the game world as having different costs. Now, A-star will always find the cheapest path, but that may not necessarily always be the shortest path. For example, let's imagine that we were to mark some region of our game world as being a rock face or a steep hill that was very difficult for a unit to traverse. We could give this region a 10 times movement cost. If we did this during the search, the A-star algorithm may well determine that a cheaper route could be found by creating a slightly longer path around the costly region. So how does A-star work? It's actually a very simple iterative search. Firstly, we're going to use one of the examples that we used in the previous lesson. The diagram on the screen shows a top-down view of a very simple scene. The red areas represent solid geometry or obstructions, areas that we can't traverse, and the white area represents traversable space. The green and blue circles represent the agent's position and the target position the agent will try to reach, respectively, in this search example. We're also going to assume that the navigation graph used is grid-based. Therefore, each grid square is a node, the position of the node being the center of the square. Now, in this example, we're also going to use an 8-way pathfinder. That is to say that an agent can move diagonally into the neighboring nodes as well as horizontally and vertically. This means then that each node can have a maximum of 8 neighboring nodes. But the nodes that are on the scene boundaries obviously may have less than this. We're also going to assume that the nodes that are solid, the red grid squares in this example, are simply omitted from the graph during the graph compilation process. That is, these nodes do not exist as neighbors of any other node. Now, on the right hand side of the screen you can see what a simple node structure might look like. Now, there are a few members here that we're going to discuss in a moment, but for now we're just going to focus on the position vector, which describes the position of the node center point in world space, and the list of neighbor references, which contain up to 8 node references to the neighbors. Now, we're going to discuss the parent node reference and the F-score and the G-score a little later, but hopefully from this simple structure you have an idea of what this graph might look like and how the nodes are connected in memory. So the search is actually a very simple loop that maintains 2 lists, an open list and a closed list. The open list will contain a list of all the nodes that we've currently discovered but have not yet processed. It contains a list of viable candidates for the next iteration of the search loop, a collection of nodes which we can choose to step into next, as it were. Now, when the search begins and we are in the first iteration of the loop, there is only one node we know about, the start node, and therefore this will be the only node that exists in the open list. That's the node the agent is currently located in. The closed list will allow us to maintain a list of all the nodes that we've already processed. As we process a node from the open list, we're going to remove it from the open list and add it to the closed list. Now, as a single node may be a neighbor to multiple other nodes, the closed list stops us from processing the same node multiple times and getting stuck in an infinite loop. When we discover a neighbor, we can simply check if it's in the closed list already, and if it is, we know we've already processed it and we can skip its processing. Of course, the closed list is going to start completely empty. Therefore, at the start of the search, at the very first iteration of our search, we have one node, the start node, in the open list, and no nodes in the closed list. As we process a node, we iterate through its neighboring nodes. These neighboring nodes are then themselves added to the open list so that they may be considered for selection as the current node in the next iteration of the search loop. So in our example on screen, we can see that in the first iteration of the loop, we would fetch a node from the open list, and in this case, it would be the start node returned to us, as this is the only node that exists in the open list at this point. Our next step would be to check that the node we fetched from the open list is not the target node. Because if the node we've just fetched from the open list is the target node, then it means our search is complete and we have correctly found our path. We then return the path and our search is over. Now, we're going to talk a little bit more about how we return the path in a moment, but for now just know that that parent node variable in our structure is how we keep track of the nodes that we're stepping through along the way, and our means of ultimately returning the path when the search is complete. However, assuming the node fetched from the open list is not the target node, we can remove this node from the open list and add it to the closed list. This node has now been processed. However, as I just stated, before we finish this iteration of the loop, we must examine all of the neighbors of the current node and add those to the open list as well, so that in the next iteration of the search loop, we've got nodes viable for selection in our open list again. However, what makes the A* search what it is what we do to the neighboring nodes as we add them to the open list. We calculate a score for them. In A* terminology, this is referred to as being the F-score of the node. Now, we're going to drill down on the details of how this F-score is calculated in just a few moments, but for now just know that this score is basically a guess as to how likely this node is to bring us to our target on the most optimal path. Now, it's a guess for the most part because we don't really know a whole lot of information about the scene at this point, but it's a guess that works pretty well. The neighbor with the lowest F-score is considered to be the best candidate to search in the next iteration of the loop, as it seems to us, at least at the moment, that this would generate the cheapest path. So once we have calculated the F-score of each of the current node's neighboring nodes and have added them to the open list, we are done processing the current node, and it's time to step into the next iteration of the loop. We always select the node from the open list that has the lowest F-score. That's how we know, for example, from the 8 neighbors that we've just added in the previous iteration, which node to select next as the current node to process in our current iteration. Now, while it might not be crystal clear to understand why it's the case at the moment, by repeating this process over and over again, we will eventually pull the target node from the open list, and our path search will be complete. So this process just happens over and over again. With each iteration, we select a node from the open list with the lowest F-score. If the selected node is not the target node, we remove it from the open list and add it to the closed list. Then we process all of its neighbors, adding them to the open list, calculating their F-score as we do so. Now, just one small detail here, which I'm going to draw down in just a moment. We only add a node to the open list if it doesn't already exist in the open list, and if it doesn't already exist in the closed list. If it's in the closed list, then it means that we've already processed it. If it's already in the open list, it means that we discovered this node earlier as a neighbor of another node, and we have to handle it slightly differently. So I'll talk about that in a moment. But there is something also very important I want to talk about that we also have to do, which is related to constructing the final path when we find the target node. And it's what that parent node member is for in our node structure. You see, as we add a neighbor of the current node to the open list and calculate its F-score as previously discussed, we're also going to set its parent node reference to the current node that we're processing. We're basically recording the fact that this neighboring node has been discovered by traveling through the current node, and its F-score calculated for that route accordingly. We're essentially linking all the nodes to one another as we go. And you're going to see in a moment that when we do eventually find the target node, we can simply loop through all of the parent nodes, starting at the target node, and trace our way all the way back to the start node by just following those parent references. And as we do so, we can add each one to a stack or some other last in first out collection, and we have our list of waypoint nodes. Now of course the position of those nodes can then be used to construct the actual agent's waypoints. Now don't worry, we're going to see diagrams of all this working in a moment, so for now just try and stay with me. So let me just go back briefly to talking about the adding of nodes to the open list. You see, when we're processing the neighbor of the current node, we don't just always blindly add it to the open list. Firstly, if it's already in the closed list, then it means we've already processed this node and we're free to skip it. We don't bother adding it to the open list again. If it's not in the open list or the closed list, then we've just discovered a brand new node on our travels. So we calculate its F-score, assign its parent reference to the current node, and add it to the open list as described a moment ago. However, it is possible that the neighboring node we're processing may already exist in the open list. If this is the case, then it means that we already discovered this node earlier as the neighbor of a previous node that we processed, and that's when it got added to the open list. Now, when this is the case, we definitely don't want to add it to the open list for a second time. What we do instead is we calculate a new potential F-score for this neighbor, but factoring in the current node that we're now processing it from. Now, if the F-score we generate from the current node is lower than the one that was already stored there, calculated when we were processing some previous node, then it means that we may have just found a cheaper way to get to that node through the current node, and we update its F-score and we update its parent reference to point at the current node. Now, don't worry if you're feeling a little bit confused at this point and are having trouble seeing the big picture. We're going to step through this process every step of the way with diagrams. So at the end of this, you're going to have this nailed and everything is going to be cool. But what we need to talk about next is we need to talk about arguably the most important part of the process, and that's the calculation of the F-score. And we also need to talk about movement costs. Now, in our example scene, I'm going to say that a movement, either horizontally or vertically, into a neighboring node has a movement cost of 10. So why am I using a value of 10? Why not 1, for example? Well, I could, but using a value of 10 is going to allow me to deal with non-fractional numbers in this example. That's going to make it much easier for all of us to follow along. Now, as this is also going to be an 8-way Pathfinder example, it means we can also move diagonally into neighbors as well. Of course, the distance diagonally across a square is greater than the distance simply moving horizontally or vertically across its width or height. So I'm going to assign a diagonal movement cost of 14. Why 14? Well, remember that Pythagoras theorem from high school? That's right, the squared length of the hypotenuse, that's the diagonal distance across a square, is equal to the sum of the squared lengths of the other two sides. Or to view it more simply, the diagonal distance across a square with a width and height of 1 is simply the square root of 2, which is approximately 1.414. Now, as we're pretending our squares are 10 units across instead of 1 unit across, we simply multiply everything by 10. Therefore, that gives us a diagonal distance of 14.14 and a load of other decimal points. But we're going to forget all about the fractional part, and I'm just going to round it up to 14 to keep the numbers simple in this example. Okay then, so let's go back to where we were. So whenever we discover a neighboring node of the current node that we're processing, we calculate that neighboring node's F-score. We add it to the open list, and we know that this will influence the likeliness of it being processed either in the next iteration or in future iterations. Now the F-score is computed by calculating the sum of two sub-scores, known as the G-score and the H-score. The G-score will contain accurate information that we've recorded along the way as we've been performing our search. This will be the cost of getting from the start node to that neighboring node that we're currently processing. Now you're going to notice in the example structure that I show on the right hand side of the screen that in this node structure I actually have a separate member where I store the G-score separately from the F-score, and this is just so that we can easily keep track of this part of the score as we progress through the search. Now the G-score of a neighbor is simply the G-score of its parent plus the movement cost from that parent into the neighbor. So in our case, the G-score of the parent plus 10 or 14, depending on whether this is a diagonal or non-diagonal neighbor. Of course, the G-score of the start node would always be 0, as in the start node we've traveled no distance at all. However, if we moved one square to the right of the start node, however, this would have a G-score of 10. Move another square right again, this would have a G-score of 20, and so on. We are keeping track of the G-score for each node as we search through the graph, and this tells us exactly how costly the path has been so far from the start node to that neighbor that we're adding to the open list. But, as already discussed, the G-score is only one half of the equation. The F-score is actually the sum of the G-score and the H-score. Remember though, it's the F-score that is the basis for node selection when choosing a node from the open list. In each iteration we're always trying to find the next node with the lowest F-score. The H-score is referred to as the search heuristic and is basically a guess as to what we try to estimate the cost of the remaining path might be. Whereas the G-score describes the cost from the starting node to this neighboring node that we're just about to add to the open list, the H-score tries to guess what the cost might be from that neighboring node to the target, the remaining distance. Therefore, if we imagine that in a perfect world the H-score was perfectly accurate, the F-score of each node in the open list would indeed describe exactly the best node to choose next, the node with the lowest F-score. Of course, we have no idea when calculating the H-score for a node what obstructions may block it further down its path, so they are not factored in. It's basically nothing more than a guess based on some kind of distance calculation. Now you can use many different heuristic calculations that will ultimately bias the way that your A-star search performs. Interestingly enough, if we omit the H-score from the F-score calculation completely, or if we just assume that it's 0 for every node, then we actually end up with another very well-known search algorithm called Dijkstra's search algorithm. This search tends to be a radial search out from the start node because we're essentially selecting our nodes from the open list purely based on their distance from the start node. But enough of that, let's get back to what we were talking about. Let's look at some of the most common heuristics that are used in A-star for that H-score calculation. So in a system that uses a nav mesh such as Unity, and in a world that is purely 3D where the agent can move in any direction at any time, in other words, in a non-gridified world, we can simply use the Euclidean distance, that is, the distance of the straight line from that neighbor node to the target node. Now in a grid-based example, we can't just do that because it wouldn't very accurately guess our remaining distance. In a grid-based system, we essentially have to move through the center point of each grid square, so the Euclidean distance would not at all describe the route or the distance of the route that we would take. It would most likely create a straight line that simply clipped across the top corners of certain squares, for example. The most popular heuristic used, especially for pathfinding in a grid-based system that allows only 4 directions of movement, basically horizontally and vertically, is a heuristic called the Manhattan method. This is simply calculated by adding the absolute values of the offsets along the x and y axis. In other words, we simply count the number of squares horizontally and vertically from the neighboring node to the target node and add those two offsets together. On the screen, you can see how we might calculate the F-score for the neighboring node that is just above the starting node using the Manhattan heuristic. As you can see, the G-score is 10. That's because to get to this node, we have had to move one node vertically away from the source node, and of course our movement cost is 10 for horizontal and vertical movement. The H-score is 50 because the target is 4 nodes away horizontally and 1 node away vertically. When we add those together, that's 4 plus 1 equals 5, and of course we multiply by 10 because that is our cost for 1 unit of horizontal or vertical movement. So when processing the start node in our example, in the first loop iteration, we would have to calculate the F-score for each of the 8 neighbors of the start node and then add them to the open list. On the screen now, you can see what the G, H and F scores would look like for all of the neighbors of the start node. Now, in this example, we are going to allow for 8 directions of movement, so the Manhattan method isn't ideal in this instance. By simply measuring the horizontal and vertical movement, we are discounting the potential cost savings we may gain from diagonally moving from one node to the next. For example, in this diagram, we can see that the true distance from the source to the target would actually be 14 using our diagonal movement cost. However, using the Manhattan method to estimate this distance, we would actually get a value of 20, a movement cost of 10 applied for both one node of horizontal movement and one node of vertical movement. This means we are overestimating the remaining distance, and therefore it's not guaranteed to always give us the shortest path, such as in this example. Now, in such instances where the shortest path is not guaranteed by the heuristic is said to be inadmissible. Having said that, however, even in an 8-way path search such as in our example, this will still nearly always give you the shortest path, and in cases where it doesn't, the offered path will be very close to optimal. For that reason, and for keeping the math simple, I'm going to still use the Manhattan heuristic in my example, even though I'm allowing for 8 directions of motion. After we have examined this example fully, I'll also give you some details on a method called the diagonal shortcut heuristic, which is admissible in an 8-way pathfinder and can be used to always find the path with the shortest distance on an 8-way pathfinding grid. But at the moment, I just want to be working with numbers that are easy to digest, so I'm going to be using the Manhattan heuristic. Okay, so let's see what this whole thing looks like with some pseudo code, because everything we've discussed so far can sound like quite a lot to take in. It can sound quite complicated, but if you look on the left hand side of the screen here, you can see the pseudocode to a function called A* that implements the entire search algorithm, admittedly in a very vanilla and basic form. But I'm sure you'll notice how small the code is and how simple it is. Now, this function, which I've called A*, assumes that you've already located the start node and the target node, and passes them into the function. So at the start of the function, we declare a variable of type node called current node, which is initially set to null. This is going to be used to reference the node that we're currently processing with each iteration of the search loop. This is where we're going to store the node that we fetch out of the open list with each iteration. Next, you can see we declare 2 lists, an open list and a closed list, both which start empty. And then you can see that I calculate the G-score and the F-score for our start node. The G-score is set to 0, obviously, because the distance from the start node to the start node is, of course, 0. And the F-score is calculated as in the equation that we saw on the previous slides, which is the G-score of the start node plus the H-score of the start node. And now, in this line of code, you can see that H-score is actually a function, which I also show on the slide, which is passed 2 nodes and returns the Manhattan distance between them multiplied by 10, which remember is the movement cost in our example. And if you look at the H-score function on the right hand side of the screen, you can see it just calculates the absolute offsets on the x-axis, the absolute offsets on the y-axis, adds them together, multiplies by 10, and then returns the result. And this becomes the H-score for our start node. Then, next, we add the start node to the open list. And at this point, our initialization is done. We are now ready to step in to the main while loop of the function, which is going to keep iterating until we either find the target node or in the case where we can't find the target node because the target node is unreachable, until we run out of nodes on the empty list. So you can see that next we create a while loop that is set to iterate as long as there are nodes on the open list. Inside the while loop, we fetch the current node that we're going to be working on in this iteration of the search. We do that by saying current node equals openList.get lowest F score. Now, this is my sort of pseudocode way of saying that whatever collection you're using to represent your open list, whether it's a sorted array, whether you're using binary heaps, whether you're using a priority queue, we're just saying here that we need to fetch from the open list the node that you contain with the lowest F score, and we assign that reference to current node. Next, you can see that we say if current node is equal to the target node, then it means that we have reached the target and we have found a path, and we now need to return that path. And in this particular pseudocode example, I call a function called construct path to do that and pass in the target node. And if you look at the construct path function on the screen, you can see that it's passed a node, and then what it does is it allocates a stack or any other type of first in last out queue, and then it goes into a do while loop. Starting at the target node, it pushes that node onto the stack, and then it sort of steps down into, or steps up, sorry, into its parent, and then it does the same again, pushes its parent, and then steps into its parent, pushes its parent, and so on. And by the time the do while loop exits, which only happens when we reach the start node, and in which case the parent will be null, so won't exist, we now have a stack that contains all of the nodes that form our path, and then we return this path. Of course, the reason I've used a stack here is just because if we then wanted to use this to sort of guide our agent, we can then pop off those nodes in reverse order, which is actually going to be the order in which we want them in. Assuming though that the current node is not the target node, we simply remove the current node from the open list, and then we add it to the closed list. We've now finished processing this node for the most part. All we have to do now is examine all of this node's neighbors and add any that are not already on the open list to the open list. So you can see that we create a for loop that is going to iterate through all of the neighbors of the current node. Remember, that's the node we've just added to the closed list. Now, for each neighbor, you can see that if it already exists on the closed list, then it means we don't want to process it, and we don't step in to this conditional code block at all. Our job is done, and we can now skip on to the next iteration of the loop. However, if this neighbor doesn't exist on the closed list, then it means that it either hasn't been discovered yet, or it exists in the open list already. Now, in both cases, there's a chance that we may need to calculate an F-score for it. Now, in the case of a node that's never been discovered yet, then definitely we want to calculate an F-score for it before we add it to the open list. In the case where there's a node that's already on the open list, we might be able to generate a better F-score for it from the current node. So either way, we want to calculate the F-score. So you can see that inside the conditional, we say that if the neighboring node is diagonally located with respect to the current node, then we set the movement cost to 14. Otherwise, it's a horizontal or vertical neighbor, and we set the movement cost to 10. And then we calculate the tentative G-score. I call it a tentative G-score because we're not quite sure whether we're going to actually use this G-score yet or not. Okay, you'll see what I mean in a minute. So you can see that in order to calculate the G-score, we simply say that the tentative G-score is the G-score of the current node, in other words, the neighbor's parent, plus whatever the movement cost is to move from that node into this neighboring node, which in our case is either 14 or 10. Now we need to see whether the node currently exists on the open list or not. If it doesn't exist on the open list, then this is a new discovery, in which case we need to calculate a new F-score for it. So we step into this conditional that calculates the G-score by setting it to the tentative G-score. It then calculates the F-score by adding together the neighbor node's G-score plus the H-score, in other words, the Manhattan distance from this neighbor node to the target node. And then it assigns the current node as the parent to this neighbor node, so that the two nodes are linked together for when we wish to trace our path back at the end of the search. Finally, we're done, so we add this neighbor node to the open list, and that's it for this iteration of the neighbor loop. However, if the current neighbour that we're processing is already on the open list, then we need to check whether that tentative G-score that we've just calculated is lower than the G-score that's already stored in that neighbour. Now, the reason we do this is because I said earlier that if we discover a node that is already on the open list, we need to replace its F-score if we calculated a lower F-score for it. However, the H-score doesn't change depending on how we get to a node, because it's just the Manhattan distance in our example from that neighboring node to the target. So the only thing that can change is the G-score. So that's why I'm calculating the G-score and doing the comparison on the G-score. So you can see that if the tentative G-score that we've just generated for this neighbor is lower than a G-score that's already stored there, then we store the new G-score. We also recalculate the F-score using this new G-score. Once again, you can see that the F-score is simply the addition of that G-score plus a call to the H-score function, which will return the Manhattan distance from the neighboring node to the target node. And we also then reassign the parent to now sort of reference the current node, the node we've just added to the closed list. And at that point, we're done, and we're now ready to move on to the next iteration of the while loop, where one of those neighbors that we've just added will be fetched from the open list, whichever one had the lowest F-score, and of course the whole thing will carry on and continue to be done until eventually current node equals the target node, and we can return the constructed path. So that's basically what A* looks like in code. You'll also notice at the bottom that I say return false and no path exists. This only gets executed if the open list runs out of nodes, because if the open list is empty, it means that we have no way of reaching the target. The target is obviously disconnected in some way from the graph. In the case of a nav mesh, you could imagine that you've told the agent to navigate to a position that falls outside the bounds of the nav mesh. So that's what the pseudocode looks like. Now, before we finish up, we're going to go step by step with some diagrams through our search example and see exactly what this code does and how it operates. So what I'm going to do now is I'm going to perform the A* search on our example scene with diagrams showing what the grid looks like and what the open and closed lists look like every step of the way with each iteration of the search. Now you can see on the right hand side of the screen I'm going to show the open and closed lists with the node numbers in, so we can see which nodes are in those lists every step of the way. And at the start of the function we've already located the node that the agent is in, node 42 in this example, so that has already been pre-added to the open list. So we step into the main search loop, and in the first iteration of that loop we say to the open list, give me the node with the lowest F-score. Now in the first iteration, as we've already discussed, there's only one node in the list, node 42, so that's the node that we're going to get back. And the first thing we do then is check that that node is not the target node, and we can clearly see that that's not the case here. So we remove this node from the open list and we add it to the closed list. You'll notice in the actual grid that once I process a node, I give it a red border, so we can easily see just by looking at it which nodes have been processed and are in the closed list. So with node 42 added to the closed list, we now need to examine each of its 8 neighbors, calculate their H, G and F scores, and add them to the open list as well. As you can see, the open list now contains nodes 31, 32, 33, 41 and 43, and 51, 52 and 53. And in the grid diagram you can see the H, G and F scores that were calculated for each of these nodes. Just so we're all on the same page, let me just pick out 2 examples so that I make sure you fully understand the H and G score calculations. If we look at node 31, it has an H value of 60 because it has a Manhattan distance of 6 from the target node. Why? Well, let's count. 1, 2, 3, 4, 5, 6 times 10 is 60. It has a G value of 14. Why? Well, because we saw when we looked at the pseudocode that the G value of any neighbor is simply the G value of its parent plus the movement cost from the parent into that node. Now, the G value of the parent, which in this case is node 42, is obviously 0, and the movement penalty from 42 into the child 31 is our diagonal movement penalty of 14. Therefore, 0 plus 14 is simply 14, giving us a final f-score of 60 plus 14, 74. Let's choose another node, node 52. This has an h-value of 50 because it has a Manhattan distance of 5. Let's test that. 1, 2, 3, 4, 5 times 10 is 50, and it's a g-value of 10. Why? Well, like I said, the g-value of any neighbour is simply the g-value of its parent, 0 in this case, plus the movement penalty, which in this case, because it's just a vertical movement, carries a movement penalty of 10. 50 plus 10 gives us an f-score of 60. So before we finish up this iteration of the loop, the final thing we have to do is we have to make sure that node 42 is now the new parent of each of these neighbouring nodes. In the diagram, you can see that I illustrate this using these transparent arrows. In this example, they all point back to node 42, as node 42 is currently the parent of all of these neighbouring nodes. Our first iteration of the loop is now complete, and those 8 neighbouring nodes are now sitting in the open list waiting to be selected in future iterations. So in the next iteration of the loop, we say to the open list, once again, give us your node with the lowest f-score. And in this example, it's now node 43, which has an f-score of 40. So we remove it from the open list, we check that it's not the target node, which it isn't, and we add it to the closed list. We also check its neighbours once again. Now this is a slightly unusual case here because we've actually uncovered no new neighbours in this iteration. Nodes 32, 33, 52 and 53 are already in the open list as they were neighbours of both 42 and 43. Node 42 we've already processed, that's in the closed list, and nodes 34, 44 and 54 are solid space, so they're either not in the graph or we just completely ignore them. So of the 4 nodes that we've discovered are viable for at least some form of testing, we have 32, 33, 52 and 53. They're already in the open list, and we saw when we looked at the pseudo code that this means that we must examine their g-values and just make sure that we haven't found a cheaper way to get to any of these nodes from the current node we're processing, node 43. Now we can see by looking at it that that's definitely the case, and that it's, for example, not quicker to get to node 32 from 42 by going through 43 first, as that would give us a sideways movement, then a diagonal movement. But let's just do the math anyway, because we know that's what our code does, and we want to make sure that we get the same values. So to calculate the tentative g-value for node 32 from 43, we would actually have to say that our tentative g-value would be the g-value already stored in the parent, 10, plus whatever the movement cost would be to move from the current node into that child node, which in this case would be 32. Well, it's already got a g-value of 10. A diagonal movement into that node would incur a further g-value cost of 14. That would give us a tentative g-value of 24. Now that's obviously not lower than the g-value that's already stored there, so we don't adjust this node in any way. We don't reassign its parent. We leave 42 as its parent, as this is still the quickest way to get to that node. Let's try another one, node 53. Now from 43, we can see that the tentative g-value would be the g-value of the parent, 10, plus whatever the movement penalty would be to move from 43 down into 53, which we know carries a vertical movement cost of 10. That would be a tentative g-value of 10 plus 10 equals 20, and the g-value stored there is currently only 14. So this is not a quicker way to get to node 53. And of course we can see that's the case. If we wanted to go to node 53, we'd go diagonally from 42. We wouldn't go to 43 first and then down. So we don't alter 53, we leave it in the open list exactly as it is with node 42 as its parent. And this iteration of the loop is complete. Now in the next iteration of the loop, we can see that there are actually 2 nodes in the open list that have matching low f-scores. Nodes 33 and 53, which both have f-scores of 54. Now in this particular case, it doesn't matter which one is going to be returned first, they're all going to get returned, so I'm just going to assume in this example that node 53 was processed first. We remove 53 from the open list, we check it's not the target node, and we add it to the closed list. We also process its neighbours. Now, nodes 42 and 43 are already in the closed list, so we ignore them, and 44 and 54 are solid space, so we do nothing with those either. And node 52 already exists in the open list as it was a neighbour of both 42 and 43. So it's currently parented to node 42. Let's just check that we haven't found a cheaper way to get there from node 53. Now we can clearly see this isn't the case, but let's run the math anyway. So the current G value at 53 is 14 because that was incurred from a diagonal movement cost from the source node, giving us a G value of 14. So in order to move into 52 from 53, that would be a G value of 14 plus a horizontal movement cost of 10, giving us a G value of 24. That's obviously higher than the G value that's already stored there. Therefore, we haven't found a cheaper route and we leave 52 exactly as it is in the open list, with 42 still as its parent. But 62, 63 and 64 are new discoveries for us. So we calculate their H, G and F values, we add them to the open list, and we assign node 53 as each of their parents. Once again, just so we're all on the same page with the numbers, let's look at some examples. The H score of 64 is 40. Why? Well, 1, 2, 3, 4 times 10 is 40, and the G value is 28. Why? Well, because we discovered this as a neighbour of 53, which already had a G value of 14. As it's a diagonal neighbour of 53, that means it incurs that extra diagonal movement cost of 14, which added to the original 14 gives us a G value of 28, which when added to the H value of 40 gives us an F score of 68. If we look at 63, which has an H value of 50, 1, 2, 3, 4, 5 times 10, it has a G value of 24 because its parent, 53, has a G value of 14 plus the incurred vertical movement cost of 10, giving us a G value of 24. So that's that iteration of the loop complete. And we can see as human beings that the nodes we want to process next are 55 and 46, and then we're at the target node. But of course, as human beings, we can see that's the route to take, but the A-star algorithm, it isn't a human being. It's just got to find its way by just crunching numbers, and it's not going to do it as efficiently as we would do as humans. Looking at the diagram, we can see that the next node that's going to be selected from the open list in the next iteration is actually going to be node 33, because that has the lowest F score of 54. So, once again, we fetch it from the open list, we check it's not the target node, and if not, we add it to the closed list. We then look at all of its neighbours and add any new neighbours to the open list. Now the new neighbours in this case are nodes 22, 23 and 24. And as you can see, they've all got their H, G and F scores shown, and 33 has been made their parent. Now node 32 in this particular case was already in the open list, so we need to check that we haven't found a quicker way to get there. Well, we haven't, because from node 33 the tentative G value calculated would be 14 plus the horizontal movement cost of 10, which would give us a G score of 24 for 32. The G score already stored there is lower than that, so we leave it as it is with 42 as its parent. And of course, the other neighbours of 33 are 42 and 43, which are already in the closed list, so we forget about, and 34 and 44, which are solid space nodes, so we forget about those too. So, looking at the diagram, and with that iteration of the loop complete, what's going to be the next node that's selected from the open list? Well, actually, there's a couple of choices. It's going to be not what you expect. You might expect it to be something over here nearer the target node, but you look at the F scores that have yet to been processed. We have node 32 here, node 41 here, and node 52 here. We're going to choose node 41 in this example. We're just going to pretend that that's the one that came off of the open list next. So we pull it off the open list, we check it's not the target node, which it isn't, and we add it to the closed list. We then process its neighbours. Okay, so node 31 and 32 are already in the open list. And so what we're going to do is we're going to check that we haven't found a better way to get to these nodes from node 41. And of course we haven't. The G value stored at 31 is currently 14, and if we were to get there from 41, that would be 41's G value of 10 plus an additional 10 moving up one node. That would give us a G value of 20, so we leave 31 alone. And of course the same is true for 32. If we were to get there from 41, it would be 10 plus the diagonal movement cost of 14, which would actually give us a G value of 24, which once again is not lower. Now if we go down to node 51 and 52, the two other nodes that are already in the open list, we'll find the same is true. You can pause the video and run through this just to double check it yourself if you don't believe me, but the G values are currently at their most optimum, and we're not going to improve things by getting to these squares stepping through node 41. Node 50, however, is a brand new discovery for us. So node 50 is added to the open list, and its H, G and F score is calculated, and node 41 is made its parent, as you can see from that little diagonal arrow there. It's got an H score of 70 because it's got a Manhattan distance of 7, 1, 2, 3, 4, 5, 6, 7, and it's got a G score of 24. Why? Well, because we discovered this node as a diagonal child of node 41, which has a current G value of 10 plus the diagonal movement cost of 14 gives us that G value of 24, and 70 plus 24 gives us an F score of 94. So that's this iteration of the loop complete. Now it's time to say to the open list in the next iteration, give us the next node with the lowest F score. Once again, there's still two nodes here in the open list which we have to search. They're going to be given back to us, but we can kind of tell by humans just by looking at this graph that these are nodes that we're not really interested in. But hey, the algorithm's going to check them out anyway. In our example, we're going to assume that node 52 got popped off the open list next. So we check that it's not the target node, which it isn't, and then we add it to the closed list, and then we process all of its neighbors. Now obviously 41, 42, 43 and 53 are already on the closed list, so we skip them. And node 51 is in the open list, so is 62 and 63. So we need to check these and just make sure that we haven't found a quicker way to get them. Node 51 currently has a G value of 14. If we were to get there from 52, it would actually have a G value of 20. 10 plus 10. So we leave that alone, we don't alter it. We leave it in the open list as is. Node 61 is actually left empty here just to show us that this is a new node discovery for us. So we calculate its H and G scores and of course ultimately its F score, and we make node 52 its parent. Once again, you can see that it's got a G score of 24 because it is a diagonal child of node 52. Therefore 10 plus 14 is 24. Now we're going to see something pretty interesting now when we look at 62, which is already on the open list. And we're going to do that test, and for the first time we're actually going to see that we do find a quicker route and make that correction to the node's score and parent. You can see at the moment that it has a G value of 28, and that's because it was discovered as a diagonal child of node 53. Therefore, we incurred a 14 movement cost from 42 to 53, and then another 14 movement cost from 53 to 62. But when examining this neighbor from node 52, we only have a G value here of 10, and because it's directly underneath 52, that means that if we were to step into 62 from 52, we would only incur an additional 10 movement cost also, giving us a tentative G value of 20 instead of 28. So in this particular case, we set the G value to this new tentative G value of 20, and we reassign the parent from 53 to 52. We've now found a more optimum route to get to node 62 with just a 20 G cost instead of a 28 G cost, which it was before. Node 63 remains unchanged. This is not a quicker route to get there. In the next iteration of the loop, node 32 is handed back to us from the open list. Most of its nodes, 41, 42, 43 and 33, are already on the closed list. 31, 22 and 23 are already on the open list. The only new node we've discovered is node 21, so let's deal with that one first and calculate its H, G and F scores. As you can see, it's got an H score of 70, 1, 2, 3, 4, 5, 6, 7, and a G value of 24 because its parent, node 32, already has a G value of 10, plus that additional diagonal movement cost of 14 gives us a G value of 24 and a final F score of 94. And once again, look at that arrow just to remind yourself that we've made this a child of node 32. Now something's quite interesting when we look at some of these other neighboring nodes, in particular node 22. This currently has a G score of 28 because it was discovered as a child of its diagonal neighbor 33, which itself was a diagonal neighbor of 42. Therefore, we currently have a G value in there of 28, but we can also see that if we were to move there from node 32, we would actually have a G score of 20. The G score of the parent 10 plus the additional vertical movement of 10, giving us a G value of 20. So we found a better way to get to 22. So we update the G score to 20 and we assign 32 as its parent instead of 33. That's that iteration of the loop complete. So now we step into the next iteration of the loop, and there's actually two nodes that could possibly come off the open list for us in the next iteration. We have node 24 and node 64, which both have the lowest F scores of 68. In this example, I'm going to assume that node 64 comes off the open list first. So we check it's not the target node. It isn't, so we add it to the closed list. Then we have to process its neighbors. As you can see, node 63 was already on the open list, so we first need to check that we haven't found a better way to get there from node 64. Well, we haven't, because node 64's G value is already higher than node 63's G value, so once we add another horizontal movement penalty of 10 onto it, that's going to give us a tentative G value of 38 instead of the 24 that's already stored there. But we can also see that nodes 73, 74, 75, 65 and 55 are new node discoveries, so we're going to need to add those to the open list as well as assign their parent pointers or references and calculate their F scores. So as you can see, all of these new nodes have node 64 as their parent, and all of their F, G and H scores are all calculated accordingly. So once again, just to be thorough, let's just choose one at random here. Let's say 55. So it's got an H score of 20, 1, 2 times 10 is 20, and it's got a G score of 42. Why? Well, because its parent, node 64, already has an accumulated G value of 28, plus that additional 14 movement cost diagonally, and that gives us 28 plus 14, which gives us 42. So all of these nodes have now been added to the open list if you look over here on the right hand side of the screen. So we're now ready to step into the next iteration of the loop, where node 55 is going to be fetched from the open list with an F score of 62. Once again, we pop it off the open list, we check it's not the target node, and assuming it's not the target node, we add it to the closed list and then process all of its neighbors. Now in this particular case, you can see that nodes 44 and 54 are in solid space, so we forget about those. Neighbor node 64 is already on the closed list, so we skip it. And node 65 is already on the open list, so we just need to check that we haven't found a lower or cheaper path to get there. That's definitely not the case, because the G value currently stored there is 38, and the G value in 55 is already 42, so it's already higher, so we know it's going to fail that test. In fact, of course, if we were to do that test, we would actually create a tentative G value of 42 plus 10, which would be 52. So we failed that test. But we also have 4 other nodes here that we've just discovered that need to be added to the open list and need to have their F, G and H values calculated, and need to have node 55 assigned as their parent. What we've actually done now is we've actually added the target node to the open list, but we don't want to bail there. We want to make sure that we've definitely extracted the target node from the open list before we return, because if we just say that the path is over once we find it on the open list, there is a possibility that we could settle for a less than optimal path. So we've now added those new nodes to the list. Now it's time to step into the next and final iteration of our search, where we're going to see that the node returned to us from the open list with the lowest F score is actually going to be node 46. And when we do that test to say, is this the target node? we're going to say yes, this is the target node, and then what we can do is we can call that construct path function that's going to step from the target node and follow those parent arrows all the way back to the start node to give us our list of nodes and ultimately our list of waypoints. So finally, just to be complete, I said earlier that when dealing with an 8-way pathfinder in a grid-based system like this, the Manhattan method is not always guaranteed to find the most optimal path. And I said that there was another method that we can use that is slightly more expensive, but will take into account the savings from moving diagonally when calculating the heuristic. So let's have a look at the diagonal shortcut method. So here is the diagonal shortcut method, and if we look at the shape of the path on the graph, we can see what this computation actually looks like compared to that of the Manhattan method, and we can see that it does indeed factor in diagonal travel. Now in this particular example, the target point Q is offset from the source point P 4 units along the x-axis, 1, 2, 3, 4, and 2 units along the y-axis, 1, 2. All we have to do is find which of the offsets is the smallest, in other words the minor dimension of the offset, which in this case is 2, and charge that at the diagonal movement cost. So in this case it would be 2 times 14. Then what's remaining once we subtract the minor dimension from the major dimension must be straight either horizontal or vertical travel, which we can then charge at the standard movement cost of 10. So you can see that that is the case here. For a length of 2, we charge the diagonal movement cost, 1, 2, and then what's left when we take the 2 on the y-axis away from the 4 along the x-axis is we have a further 2 left, which we just charge at the standard movement cost of 10, 1, 2. So if we look on the right hand side of the screen, we can see what the code looks like. Now we start off very similar really to how we do with the Manhattan method, and we calculate the absolute offsets between the 2 points along the x and y axis, and I've stored these in variables x delta and y delta. But then we check which one of these deltas is the largest, because that is going to determine how we do the next calculation. Now in our example we can see that the x offset is larger, 4, versus a y offset of 2, and therefore if you look at the code we can see that this first conditional would be triggered. So if x delta is larger than y delta, then we take y delta, which is the minor dimension of the offset, and we multiply it by 14. In other words, we say that this is a diagonal movement. But then what we do is we add on to that by subtracting the minor dimension from the major dimension, and what's left we multiply by our movement cost of 10. Remember, 14 and 10 are just the movement costs that we used for 1 unit of travel in our example. But in the case where this isn't true and the y delta is bigger, then we do the same in reverse. This time we take the x delta and multiply that by 14 and add on to that 10 times the difference between x delta and y delta. And that brings this lesson to a close. We've had an exhaustive look of how the A-star search algorithm works, and you should feel pretty confident now, even if you had to go away and implement such an algorithm yourself. Now in the next lesson we're going to see that Unity does all of this for us, which you might think makes this a waste of time, but like I said, this is good knowledge to have and we may need it down the road. And I also think it's pretty good to understand what is happening behind the scenes, because on big graphs with lots of obstructions, an A-star pathfinding search still can be very expensive. So we need to know that when we request a new path, we're doing something pretty costly in Unity. Now in Unity the pathfinding is now done in a separate thread, I believe, so things are certainly made much more efficient because of that. But we still need to be aware that pathfinding is expensive. Of course, once we found the path, having the agent follow that path is actually very trivial and not computationally expensive. So it's just that initial path search which is going to rack up some CPU cycles. Okay, so in the next lesson we're going to look at building nav meshes in Unity and how to get a nav agent to follow a set of waypoints. I'll see you then. Bye bye.